There are 5 types of reactions that are classified according to what happens in them. So a synthesis is kind of taking 2 simple things and putting them together. Sometimes it's also called a combination. Decomposition is the opposite of that, so it's just splitting something apart. Combustion is when you have something reacting with oxygen. Single replacement is when one element replaces another element in a compound, and double replacement is when 2 ions are going to just switch places in the compound. So a synthesis or combination reaction is one in which a compound forms from simpler materials. So you'll have 2 elements as your reactants, and then they will get put together as your products. So we have carbon and oxygen reacting to form carbon dioxide. So we're going to predict the products here of a synthesis reaction. So we have solid strontium and iodine gas. Remember that iodine's a diatomic, so it'd be I2. When those go together, it's going to form strontium iodide. So whenever you're putting something together, you have to balance the charges, just like you did with naming. If I said, what's the name of strontium iodide, you would know that you have to balance the charges. So same thing. So SrI2. And then that one is balanced chemically. Lithium metal and oxygen gas. So lithium metal, oxygen gas. Oxygen is also diatomic. And since it says gas, I'll throw it in there. It really doesn't matter. So that's going to combine to form lithium oxide. Lithium is a +1. Oxygen's a -2. So lithium oxide's Li2O. And then I would need a 2 in front of the lithium. Oh, nope, just kidding, sorry. I would need a 2 in front of the lithium oxide to balance oxygen and a 4 in front of the lithium to balance the lithium. So subscripts that are in your reactants have nothing to do with subscripts that are in your products. The fact that this is a 2 and this is a 2 is a coincidence. They are 2s for 2 separate reasons. As you can see, it was O2 as a reactant in my second one, and then it was just O as a product, because when you balance the charges of lithium and oxygen, you need 2 lithiums and 1 oxygen. The opposite of asynthesis is a decomposition. So decomposition is when you have one compound and it's breaking down into its elements. So water breaking apart into hydrogen and oxygen, and you're always going to just break these into their elements. Doesn't matter what compound you have, just split it up into its elements. So sorry. So if we were doing aluminum bromide decomposes, you're going to write the formula for aluminum bromide. Aluminum's a +3. Bromine's a -1. So AlBr3. Decomposes, we're just going to split it into aluminum and bromine. When elements are by themselves, of course, you need to think about or check if they're diatomic. Aluminum is not. Bromine is, so it becomes Br2 because it's diatomic. And then to balance, you would need to do that. Okay, so that's a decomposition. In a single replacement reaction, sometimes called a single displacement reaction, one element replaces the atoms of another element in a compound. So with a single replacement, you're always going to have a single element plus a compound as your reactants. So in this case, I have my compounds copper chloride and my single element is aluminum. And the aluminum is going to replace the copper. It's going to push the copper out of the way, bond with the chlorine, and then you're going to have the copper by itself. So that's what happens in a single replacement. One element kind of pushes the other one out of the way, and then the element that got pushed out of the way is now the one that's by itself. In these single replacement reactions, a metal is always going to replace metal, and non-metal will always replace non-metal. And to determine if a single replacement reaction occurs, you have to look at this thing called the activity series. So this is the activity series. This is on your periodic table. At the top are the most active elements. At the bottom are the least active elements. So an element can only replace a less active element. In the example we just did, we had aluminum replacing copper. So here's aluminum, here's copper. The aluminum can replace the copper. You can go down, you can't go up. And we'll look at that in just a second. So sodium plus aluminum chloride. First thing we have to do is consult our activity series. So here's sodium, here's aluminum. Metal replaces metal, so sodium's going to try to replace the aluminum. So it's going that way, it's going down, so it can. So the sodium will replace the aluminum, and the aluminum will be by itself, and the sodium will bond with the chlorine. And then to balance, it would be like that. In the second example, we have bromine. Bromine's a non-metal, so bromine is going to try to replace fluorine because fluorine's a non-metal. Non-metal replaces non-metal. So I have to consult the other, oops, sorry, wrong way. I have to consult the other activity series. Bromine is going to try to replace fluorine. It's going to try to go that way. You can't do that. So if that occurs, if something's trying to replace something more active than it, there's just no reaction that occurs. And so that is what you would write. In my last one here, hydrogen, now you're like, hydrogen's a nonmetal. Keep going the wrong way, sorry. But hydrogen is on the activity series of metals right there because it forms that +1 ion. So hydrogen is going to try to replace zinc because they're on the same activity series. So hydrogen is trying to replace zinc. It's trying to go that way. It can't. So we're just going to write no reaction. Double replacement reaction, you're going to have two ionic compounds as your reactants. And the cations are going to switch places. They're going to switch partners. So the cations always come first in the formula. So the lead and the potassium are going to switch partners. Now, because they're switching partners, they're both switching. We don't consult the activity series for that. That's only for single replacement reactions. So the lead and the potassium are going to switch partners, and then the lead's going to be with the iodine, which is why I get lead to iodide. The potassium is going to be with the nitrate. Okay. So we're going to write a balanced equation for the reaction of sodium sulfate and calcium nitrate. So of course we first have to get the formulas of sodium sulfate and calcium nitrate. So sodium sulfate's Na2SO4. Calcium nitrate is CaNO32. And then again, the cations, the sodium and the calcium, are just going to switch partners. So the sodium's going to go with the nitrate. Sodium's a +1, nitrate's a -1, so it's just NaNO3. The calcium's going to go with the sulfate. Calcium's a +2, sulfate's a -2, so it's just CaSO4. To balance this, I would just need a 2 in front of the sodium nitrate. Oops, I didn't make that 4 little. So in this last one, we have strontium and lithium that are going to switch partners. So lithium's a +1, chlorine's a -1, so it's just LiCl. Strontium is a +2, phosphate is a -3. So you need 3 strontiums and 2 phosphates for the charges to balance out. Balancing wise, let's see, I'm going to need a 3 there and a 2 there and a 6 there. Our last type of reaction is called a combustion reaction. In a combustion reaction, one of the reactants is oxygen. So technically, the second one here is classified as a combustion reaction. You could also classify it as a synthesis reaction. So either way you classify it is totally fine. But the more common combustion reaction that you're going to see is a hydrocarbon. So that's a hydrogen and carbon compound plus oxygen. And it is always going to make the same products: carbon dioxide and water. These are always the products of a combustion reaction between oxygen and a hydrocarbon. So when you're predicting combustion, super easy. So combustion of propane, C3H8, it's always plus O2 because that's what combustion means, always yields CO2 and H2O. The balancing for this one is 3, 4, and 5 there. Methanol, combustion of methanol, CH3OH, same thing, is going to react with O2. It's always going to produce carbon dioxide and water. Balancing this, let's see, I have 4 hydrogens on my reactant side and 3 oxygens, so there's an odd oxygen out. So probably I'm going to need a 2 there, a 2 there. So that's going to be 6, 8 hydrogens, so 4 there, 4, 8 oxygens. I got 2 there. Ooh, that was a hard one to balance.